Hi, everybody. My name is Joel Van Epps, and today I'm going to be going over a topic from the FE exam. That topic is material properties in processing. Um, I have a little slideshow I'm going to share the screen right now. It can be on the screen share. And bring this in. So this topic here has 7 to 11 questions on the actual FE exam, broken down into the categories listed below. Today I'll be going over probably 4 or 5 of these topics. So starting out with a stress strain diagram, one question that might arise on the exam is pointing out where a certain strength or fracture occurs on this diagram. So it's really good to go through and just know your basics so that when this question arises, you can solve it very quick and move on to one that may take more of your time. So over here on the y-axis, we have a stress, x-axis, we have a strain. If we take the slope of the elastic region here, that's how you get your Young's modulus or E value. Your elastic region lasts from 0.0 up to your yield strength. After the yield strength, strain hardening occurs, starting in the plastic region. Ultimately, your ultimate strength is reached, and then after necking occurs, and eventually another important diagram underneath this topic is our SN diagrams. SN standing for stress life diagram. Really be broken down into finite life and infinite life, where finite life is broken into 2 more subcategories of low cycle fatigue and high cycle fatigue. The low cycle fatigue is between 0 and 1,000 cycles, where after 1,000 cycles up to 1,000,000 cycles is your high cycle fatigue. Anything beyond that point would be considered infinite life and most likely a successful test. Anything below this curve here is considered a pass, while anything that lies up on the outskirts out here would be considered a failed test or a failed part. Under the next category here, ferrous versus non-ferrous metals. Ferrous metals contain iron, while non-ferrous lack iron. They have similar properties, however, when it comes to corrosion resistance and weight to strength ratio, non-ferrous metals typically are better. However, ferrous metals are more recyclable and ductile. These ferrous metals would include stuff such as steel, stainless steel, cast iron, while non-ferrous metals include zinc, copper, and nickel. Your ferrous metals are typically used today in automotive components, while your non-ferrous metals may be used for like tooling or electrical connections. Now we'll move on to our first sample question here. This was one question, very similar question to what I saw while taking my exam. Which of the following materials is most conductive? And off basic knowledge, you may know this question. It's very simple, straightforward. You can typically go right into the FE handbook and find an answer that you like. So we'll be using the FE handbook here. Grab this on over. And we can search up this question. So if we control F, and let's see, what would be this? Probably conductivity. You see, it's quite a bit of conductivity in the FE cheat sheet. And we'll just look for something that is of use to us. So right here, this might be it. Yep, our heat conductivity chart here with our material properties of metals. So if we go back to the question. Which of the following materials is most conductive? Copper, nickel, tungsten, or aluminum? So if we look here, we have aluminum right at the top at 236. We go down a little bit to copper at 403. So we know copper is more conductive than aluminum. Nickel at 94, not really conductive. And we also have tungsten at 177. So we go back to a slide. And we will see our results here. We lead to copper. So that is how we would go in and search on the FE handbook for a simple question like this. These are very important ones to get right as we're trying to get past the exam and every point counts. So now we'll move on to a more intermediate question here that involves a thick centered crack inside of the thick plate. So the question, a thick centered crack plate of an aluminum alloy is 100 millimeters wide with a crack length of 60 millimeters. If it fails at an applied stress of 200 megapascals, what is the fracture toughness of the end? So when reading that first question, what stands out to me is fracture toughness. So what I would want to look up in the FE handbook would probably be fracture toughness. But the second part of the question says then, what value of applied stress would be needed to fracture an infinite plate with the same crack length? Our Y value for this is given 1.1 for a center crack. And Y equals 1 for an infinite plate. All right, so our givens, we have 2A equals 60 millimeters. 2 times our width equals 100 millimeters. Stress 200 megapascals, and our Y 1 point. So let's go. Right now I have the equation given as K1C, which is your fracture toughness, equals Y times sigma times the square root of pi, which A is your. So let's go into the FE cheat sheet one more time. And we need to search up fracture toughness. Right there it is. So you can see here, you have an exterior crack where Y equals 1.1, an interior crack where Y equals 1. So that's where I got the Y equals 1 from. We know that we have a center crack. It's in the middle of our profile where Y equals 1. But if you take a close look, 2A is the total crack length. So what we want to solve for is just A. So if we go back to the question, we are given 2A equals 60 millimeters. So 2A equals 60 millimeters, meaning that A in our equation is actually equal to 30 millimeters. However, one thing we want to pay attention to is the units given in the answers that you can select from. So what I'm gonna do is I'm gonna take this 30 millimeters right now, and I'm gonna change this to meters. So we have 0.03 meters. So now it's basically plug and chug from here. So we have K1C is equal to 1.1 times the sigma stress 200 megapascals times the root of I A, where A is 0.03. So this ends up being 67.54 megapascal root Fourier differential calculus would be the answer to the first question now. Now, we would like to go back and figure out what this would be in an infinite plate. And for an infinite plate, y is equal to 1. So now we want to find what value of applied stress of it for an infinite plate would be equal to 67.54 fraction tons. So now we just want to rearrange this equation to solve for sigma. So we have 67.54 over 1, which is our y value, root 0.303 meters. And that should be equal to applied stress. And if we take this to a calculator, we get approximately 220 megapascal. So I would say the main challenge with this is making sure that you can find the right equation and take the information given in the FE handbook and actually apply to the question. Put this down now. And we will move on to question 3, which involves a phase diagram of tin and lead, where the composition is of tin that we are trying to solve. So tin alloy has a weight composition of 50% at a temperature of 175 degrees Celsius. What phase is present? And the second question, what are the weight percentages of the phases present? So, what's our givens? Our givens are the weight percentage of 50% and a temperature of 75 degrees Celsius. So, let's mark that here. diagram, we want about 50 degrees or 50%, 50% composition, and we want roughly 175 degrees Celsius. So if we extend our lines here, we can see that we will end up we will see that we end up we will see that we right around this point. Now, this point for this problem is going to be x. X value right there. But we can see our x value lands in the alpha plus liquid phase. So that will be our answer to part A. So part A, we have the answer of alpha plus liquid. Now we want to find the actual weight composition of our phases. So we want to find alpha and our liquid. So what we will do is we will go to the we'll go back into the cheat sheet now. This. We'll go here. At the cheat sheet, and this technique is called the lever. This should take us right into the phase diagrams. So we can see here we have a pretty similar diagram, more basic, but we have our weight percentage for alpha down and the weight percentage for beta. So we're going to use a very similar equation to solve this. We will solve part B. We put our x value up here. Okay. That's our x. Now what we need to find is our x value for liquid and our x value for flow. So we'll extend this back over here. This is where alpha is. Oops. A little bit more straight line here. Ends up somewhere right around, I would say 18% composition. Our x was obviously given at 50%. Our liquid, we can draw it over to the liquid phase and bring that right down. And it's roughly, let's call it 62. So 60. So 62. Now it's time to take the lever rule and come up with our equations. So equations will be for the weight percent alpha we are looking to basically figure out the percentage just inside of this alpha plus liquid. So you can see our alpha should be a lower percentage of 10, since 10 is our beta over here on this side. This would be our percentage of 10, while this one would be our percentage of liquid. So if we go in and the equation, we will take from our x value, we are looking x minus our L value here. So we have our XL minus X over XL minus. So what this will give us is our percentage this side of the diagram, and to find our percentage here, we will be using WT% of the liquid is equal to X alpha value of 18 over the XL of 62. So if we plug these in, we have XL 62 minus 50 of X value over 62 minus 18. And with this, we should get around 27% as our percent weight alpha. And if we go in to find the percent weight of liquid, we have 50 minus 18 over 62. It's that same 18 from the if you figure out one, it should add up to 100%. So this one, after calculating it, we end up 73%. That's a good sign, showing that we have a confident answer. So clear this, pause if needed, put it on Jones, and we will move on to the next slide. All right, so that was it for material properties in processing portion of this. I wanted to throw in one more bonus topic, as while taking my exam, I noticed that there were 2 or 3 questions just off of this slide. So it's very important to know your trademarks, trade secrets, copyrights, and patents. These questions may be multiple choice. Compare and contrast, or pair up a trademark with a symbol or a device that is associated with a good. So it's really good to know these definitions going in. And I think this topic here is worth studying, as it's quick, easy points, as long as you know the definitions and what you're looking for. So that is all. Thank you guys for watching. Hope this video helps. And we will see you next time.